Very good morning, everybody. We shall get going with this course. I was going to share my video for you, but it seems to be my webcam seems to be complaining this morning. So if I get that working, I will put it on and say hi. I will leave it off for most of the course anyway, just to save distractions. But my name is Adrian Jackson. I'm from EPCC at the University of Edinburgh. And I'm going to be giving this course today, which is an introduction to ARCHER2 for data scientists, whatever data scientist means. So we'll go through what we're actually intending to do here for this course. It's a mixture of lectures, so me talking to you and then trying things out on the system, so practical exercises. And as such, you should have an account on ARCHER2 to be able to do those exercises. You'll have had an email from Claire, our training organizer, about how to get such an account. So if you don't already have an account on ARCHER2, please do sign up for one so we can do the exercises on the system. If you already have an account on ARCHER2, you're already a member of the system, then that's fine. You can use the account you have. You don't need to sign up for a new one particularly for this course. And now I should also say these lectures and practical sessions have been recorded. We found this useful to be able to sort of maintain a version of the course that people can view later, come back to, or view if they couldn't attend. If you have any problems with that, let me know. It's also would be great if you ask any questions as we go along. So there's a couple of ways we can ask questions I'll come back to, but you can just unmute yourself and speak to me. You can also type a message in the chat, and then there are some resources we can use as well, which I will look out and put in the chat. So there's like a hack pad, a place you can write online to share questions as well. Okay. Assuming you can all hear me okay, I shall keep going. So all the material we're sharing today is going to be available online. You can use and reuse it as you like, as long as you acknowledge where it came from. And so what is ARCHER2? Actually, I need to update this slide because this was a slide written for the beginning of a service. It's not quite a new UK National Supercomputing Service. It's relatively new, but it's ARCHER2 is one of a line of computing services provided by the UK Research Councils, and particularly in this case, EPSRC, for academics, primarily for academics to use for their research. It's hosted, operated, and supported by ourselves at the University of Edinburgh, with hardware supplied by Cray. So it's a Cray system run in Edinburgh for the UK academic research community, mainly in the EPSRC sciences. Alongside the actual system and running the system, there's also funding for various things. And one of those is for training sessions like this to help people use the system, help people use the system efficiently, and to improve people's code and use of the system in general. So this is a sort of introduction course. We also run a whole range of more advanced courses teaching you how to program parallel applications, or to use particular packages, or to optimize applications so they perform better on the system, these kind of things. And so you found this course, you clearly have some knowledge of ARCHER2 and its training program, but it's worth having a look at the kind of courses we run. We have a back catalogue of courses and all the materials are online. What does ARCHER2 actually look like? Again, these are slightly old pictures now, but this is the system where it's fitted out in our machine room. On the left is the sort of deployed system with all the nice shiny pictures and panels on it. On the right is what it looks like underneath that, with all the cabling and the cooling and all these kind of things connecting it up. But basically, it's a large number of servers, high performance servers, connected together with a nice network, high performance network, and a high performance set of file systems running out of one of the machine rooms up in Edinburgh. As I say, there's a lot of support and resource materials online for this, including all our training courses, but also quite comprehensive documentation on the system. So these can be your first port of call if you have any problems. We also have a full sort of support service as well to help people with their system as well. So what I would call a help desk, but I think these days we call a service desk. As I said, my name's Adrian Jackson. I'm a researcher at EPCC. So I do high performance computing parallel research, but also help out on things like this and supervise PhD students and master's students and those kind of things. If you have any questions out with the course, then please do feel free to email me, or the service desk. Either is fine, but if you want to just email me, that's okay. My email's on the slides. And it may be a little bit premature, but with all these courses, we look for feedback on how the course went from the attendees. So there will be a feedback form at the end of the course for you to fill out. In general, we just need the overall rating good to bad, but there are more detailed feedback you can provide as well. So I will remind you again at the end of the course, but when we've done the course, it would be nice if you can fill that out, because that's useful to us to know, would it be nice to change bits of the course? Are there things that you were looking for but didn't get? Were there things that were particularly good? And if you're really interested in high performance computing, we at EPCC do run some other more involved, more in-depth things as well, including master's programs in high performance computing and high performance computing with data science, and online master's programs now, which spread across a couple of years. So if you really like high performance computing, there are other things you can do here. Okay. If you sign up for an account with a project for this course to give you access to a system to run the stuff on this training course today, that gives you access to ARCHER2, and it gives you a small amount of time on the system. And these course accounts will stay around for a little bit. So I think, as it said here, Claire, if she's still around, will correct me if it's now changed, but generally you get a couple of weeks after the end of the course finishes to still have access to the system, try out any things that you didn't get around to in the course, copy data off, these kind of things. It's always worth remembering that these accounts won't last forever though. So if there are things we do on the course you want to keep, you need to copy those files, that data off the system as well. In terms of the actual material of the course, for other slides, practical exercises, these kind of things, that will be online for much longer. All our courses are given under a code of conduct, which is specified on the ARCHER2 website here. And basically, there are details of what we expect there, the kind of behavior people should exhibit and shouldn't exhibit. And if anything goes wrong, or you think anything has been contravened in this code of conduct, then there are on that web page ways of reporting such incidents. So just to be aware of that. Okay, we're coming to the end of this now, but the other part of the funding, one of the other parts of the fundings that comes with the ARCHER2 service is something called embedded CSE support, or ECSE. And embedded CSE support provides money or time to optimize people's codes. So I know we haven't even started using the system here, and we've not even talked about applications or anything like that. It sounds like we're getting a little bit ahead of ourselves here. But it's always worth mentioning to our people who attend our training courses that there is this resource available, because it's a unusual resource in UKRI funding landscapes. It's something where you can ask for time or ask for money to employ somebody locally to optimize an application, or to provide help getting your application onto the system, onto ARCHER2. So the funding councils really recognise that efficiently using large-scale parallel systems like this is hard, and so they provide these set of funding calls for small projects to optimise either an application, a particular kind of part of an application, or the use of a system for various communities. And so if there's anything, if you've got an application but it's not running well on ARCHER2, or you don't know how to port your application onto ARCHER2, then it's worth having a look at these kind of things through this ECSC webpage, or coming back and having a chat with us to see if there's any funding available or any support available for yourselves. Okay, so that's sort of the introduction, the high-level stuff, and the sales pitch. Let's actually get onto the course now. So we're going to be looking at how we use ARCHER2 for things that we may call data science. And obviously data science is quite a nebulous term. It covers a lot of things. But we're looking here at applications that have not traditionally been large-scale parallel applications, not traditionally been users of large-scale systems, and generally we're looking at things that come from slightly different programming communities. So specifically the way we chose to take this course was to look at doing how will you efficiently use Python and R on a system like ARCHER2, because Python and R tend to be heavily used in the data science community and the machine learning community for these kind of applications, for this kind of work. But in general, they're often designed or run on small scales on your laptop, on your desktop, on a single core with small data sets. So here what we're looking to see is how could you use things that are written in Python or R on a system which here we see ARCHER2 has got nearly 6,000 servers, or what we call nodes. Each server has 128 cores in it. So it's nearly 750,000, or it's probably more than 750,000 CPU cores in here. And how do we get onto that and use Python efficiently there, R efficiently there, and scale Python and R up to large data sets or to things that take a long time to run. Because it's a large-scale parallel system, there's some complexities to it. One of them is that we don't ever get direct access to the compute nodes, to the compute servers where our jobs run. It's all the access is done through what we call a batch system. And the batch system we use here on ARCHER2 is called Slurm. And we'll come back and have a look at how you use that a little bit. But that's how we run our jobs on the system. So when we access ARCHER2, we log directly in to a small set of compute nodes called the login nodes, and we can do lots of compilation, setting things up there and transferring data there. But when we actually want to use the resources for our applications, we run it through the batch system, through Slurm, and it submits our jobs and it takes them and runs them on the compute nodes for us. We also have a range of storage systems, places that data is held on ARCHER2. And this is because we want obviously applications to run very quickly on the system. We don't want there to be any bottlenecks, any places that there are issues in terms of performance. And one of those places can often be the file system, reading and writing data from the file system, from storage. And so we have an optimized storage system for the applications to use when they're running. That's called the work file system. The work file system is high performance so that it doesn't slow down the compute job when they're running. But because it's high performance and large, we can't, for instance, back that up. We can't take the data on there and replicate it and make sure it doesn't get lost. So we provide also a home file system like this, and that's where you can store programs or store small amounts of data that you need and that is backed up and maintained over time. Why do you care about this complexity? Well, the way the system's set up, the home file system is what you log into when you first get there, and you end up in a directory called something like home TA105, TA105, and then your username. Assuming you've joined with an account in the TA105 project, and you can do what you like there, but when you need to run jobs, we have to run them and have all the data and all the application code on the work file system, which is set up in exactly the same way. If you've got a directory called /home/TA105, TA105, and your username, and then the work file system is exactly the same. It just starts off with work. So the only reason that I go into this complexity at this point is that when we start running jobs, if we try and submit a job from the home file system, it will submit, but it gives a warning, and then it won't necessarily run correctly because the place you're submitting it from isn't accessible from the compute nodes. So you have to submit things and run things from the work file system, which means that when you log onto the system, when we come to do the practicals, you're best to go straight to the work file system and do everything there. Okay, and we just mention this now because it often catches people out. Even if we go over it and say the work file system is not accessible, it's not always entirely clear to people. So it's worth just stressing this one up front. Okay. What we'll do here is we've got a course for today. We run all the way up till 5 o'clock, although in reality, 5:30, sorry, but in reality, the last exercise can be done at a later date. So, you know, the last lecture will go till about 4:30, 5-ish. And we've split today across a couple of themes. The first one this morning is looking at how you use ARCHER2, so how you get on the system, what the hardware looks like, how you run jobs, how you make sure jobs run in a sensible way on the system, particularly using file systems and placement of jobs on the system so that you get the best performance. Then we'll have a break. After that, we'll talk about containers. And so this is how do I install my own software on the system if it's complicated or not already there. Now, a lot of things we compile the code and we run it on the system as normal. And that works well for applications that are sort of written in C or Fortran or C++. But applications that have more complex dependencies need lots of libraries, need lots of different languages, or large-scale Python things may be harder to install on the system. And there we can use this concept called containers, which lets us effectively run our applications inside a mini operating system designated for that application, and that can be easier to install software inside, easier to port in more complex software onto the system. So we'll have a look at that, and then in the afternoon we'll look at Python, specifically how Python is set up and how R is set up on the system, and how you can use it to your advantage. So this is a ARCHER2 introduction to ARCHER2 for data scientists, but we're not really teaching any data science things. We're just teaching you how you use a system from common data science tools, Python and R, how you bring on new applications to the system if they're complicated to port and install, and what ARCHER2 looks like, and what are the things you need to consider to get good performance out of a system like ARCHER2, particularly for applications that are in the data science or machine learning arena. As I say, we have exercises all the way through. We've got 5 exercise sheets, and the material for this is all online in a GitHub repository, which I shall show you. But this just recaps what I was saying. We want to by the end of the course, we want you to be able to hopefully know what Archer is suitable for, and then by corollary, what it's not suitable for. how you run things on ARCHER2, how you bring new software into ARCHER2, and how to use the hardware as efficiently as possible. We're not aiming to teach you how to undertake data science in general, or this is not a specifically Python or R course. It goes across a few things, and we're focusing on the ARCHER2 hardware, on containers and Python and R. Obviously, there are other things you could have taught on a course like this, on an ARCHER2 data scientist course. These are the topics we thought were probably most useful and most important for people to use. If there were other things that you want to be covered, then do let us know. You can either let me know or through that feedback form. That's always useful information to have. And finally, for this introduction, hopefully this course will be useful to you and at some level enjoyable. Please do ask questions as we go along. We go through quite a lot of material. It won't all be clear. I will try and make it as clear as possible, but any questions at any time are helpful. Or if as I say, if there's things we're not covering, which are slightly adjacent to the things we're talking about, Python, R, containers, the hardware, then just jump on and let me know. We'll try and go through that. Any questions? So if not, what I will do is I will just share the website briefly. So just so we all know we're in the same place. Thanks, Paul. So this is the ARCHER2 website. And I'm sure you're all completely familiar with this because you're here on the course. So, but just in case, we're in training. We're on upcoming training, and we are ARCHER2 for data scientists. Here, this line here. If you go into there, you'll see this timetable for today. Okay, but this doesn't have the link onto the material we're using. So let me just copy the link across. So we've got a GitHub repository. Now I have too many tabs open to find. Here we go. The actual GitHub repository we're using for this course today, and I'll put this in the chat here as well, so you can copy it. It will also be in the slides coming up. Is this one here? So it's github.com/epcced/archer2-data-science, and we can see here that we have the lectures that I'm giving today are all here in PDFs if you want to go through them yourselves. And the exercises we're doing here are all in these PDFs: Practical 1, Practical 2, 3, 4, 5, with some source code associated with them. Once you're on the ARCHER2 system, you can clone this. You can get the data down onto the system, because I get these exercises and all the other things down the system using this command here, this git clone the repository, and that will let you get the exercises and source material that we're going to use in the application. There is also, and I've just misplaced the link. Let me just find the link for the hackpad, where you can also put in questions, comments, these kind of things in a more interactive way than in the chat here on the system. So give me 1 second and I'll pull that up. Okay, this is a chat pad location as well. I put that into the collaborate chat so you can find that as well, and that looks like this. So you can see here that you can type things in here. I'll put the GitHub location in there. Not that you need it in multiple places, but it just shows you if you've got anything you want to stick in there, or if there's things that are not working, or little snippets of code and things, you can put it into this hackpad. It can be useful to share things across the group, or with me, or with, I should have said as well, my colleague William here is online to help with any issues we have as a course going on as well. So there are multiple people here as well as to look after you. If you have any problems accessing ARCHER2 with any of the material or any questions in the meantime, even when I'm speaking, William's around. So please do feel free to jump on the chat if there's anything going on. Okay, so we shall, as I say, if you've got any questions, just give me a shout. In the meantime, I'll move on to the first lecture. Give me a second and I'll get that loaded up and we can get going. It should come through in a second. Yeah, so if you have thanks for the question. If you've got a account already in the TA100 project, so I think that probably means you're on a previous course recently, then you can use that one for now. Yeah, if that is still active. For this course, so for some courses we run, we set up special reservations on the system so that you can submit jobs in the practical exercises and get the results back very quickly. For this course, we don't need to do that because there's a set of queues set up on ARCHER2, which we'll come to see. I'm getting ahead of myself a little bit here, but which let you run small jobs very quickly anyway. So we don't tend to need a reservation. So in this case, you don't need to use the project account for this specific course for any particular reason if you already have an ARCHER2 account in another guise. If you don't have an ARCHER2 account, then you should sign up for the TA 105 project. So when we come to the practical session at I think it is 11 o'clock, which no doubt will be late, but we can get onto that practical example and play around with that. And of course, if you're having problems getting onto the system, then just let us know, or when we come to that practical session, we can then get up and give you a hand doing that then. Okay. So here, this lecture, we're just going to talk about what ARCHER2 is, what the hardware is, and as I say, the places where where performance variations can occur, the things that you need to consider for performance. So, as already mentioned, ARCHER2 is a large system. It has nearly 6,000 compute nodes. It has a high-performance network connecting them all together. And it has a bunch of different file systems you can use as well. To support the system, it has some login nodes with the way we interact with it. And it actually has what we call some data analytics nodes as well. So this picture here on the right-hand side is aiming to sort of show that we have all the compute nodes when we log into a system, we can log into a small set of login nodes. Any jobs we want to run, we submit through the batch system, and it runs here. And we can see that the login nodes, they can access all the file systems. But the compute nodes, they only have access to these work file systems and this solid state, just the storage file system here. Most of this complexity you don't need to worry about. There's a couple of things that are interesting here. One is, of course, we have these work file systems, so any work we're doing on the compute nodes needs to be on the work file systems. We're using a batch system to submit our jobs to the compute nodes. And there is actually a third file system called the solid state file system, which gives it even better performance but is smaller, which is also potentially available for your jobs, but people don't get access to it by default. So this is here for applications where you know I/O performance, reading and writing files is really important for you. You can ask for access to this. And actually, I need to update my pictures because this solid state file system is also accessible from the compute nodes and from the login nodes. But that's around as well. So there are, if you're going to bring an application, and quite common for data analytics, data science applications to be quite heavily dependent on I/O performance, on reading and writing files, then the solid state file system may be a place which can give us some optimization for your applications. As it says down here, the home file system is reasonably big, a petabyte, and you have access to the login nodes and these small data analytics nodes here. The data analytics nodes are not really very well named because there's only 2 of them. You can't do large-scale data analytics on them, but they're really there for moving data on and off the system, for things that you can't run on a compute node, or you don't want to run on a compute node, but are too long to run on the login nodes. So it's things like packing up or unpacking large data structures, archives, zip files. It's doing a bit of post-processing on data which doesn't need large amounts of compute, but needs access to the data. It's copying large files or large amounts of data on and off ARCHER2. That can all be done through these data analytics nodes. But in general, if you had a big data science, machine learning job, you'd be running it through the compute nodes. ARCHER2 is not ideal for machine learning because it doesn't have GPUs. So it's not a system that has GPUs in it. You can run any machine learning on a system like ARCHER2. You just don't get as good a performance as if you were using a GPU system. So what does ARCHER2 actually have? Well, it has these compute nodes. Each compute node has 2 processors in it. They're AMD EPYC processors, but you don't really care about that. And each processor has 64 cores. And then the majority of the compute nodes have 256 gigabytes of memory. So you can think of that as 2 gigabytes of memory per compute core. They're not restricted in that way. You can use all the memory from one core, but that's what they have. And then a subset, 300 of the 5,860 nodes have more memory. So we've got 512 gigabytes. So we've got 4 gigabytes a core. Again, most of this complexity you don't care about. It has a node. That node has 128 cores. You can use that 128 cores for your applications. That's really all you need to know. But there is lots of complexity inside these processors. In fact, each processor has groups of 8 cores, and each processor has sets of 8 cores attached to 64 gigabytes of memory each, and etc., etc. That can become important when you look at optimizing the performance of applications. So making sure that something that runs on this processor ideally accesses the memory which is closest to it will give it the best performance. And something that runs on this processor inside the node accesses the memory that's closest to it will give it the best performance. Making sure you run something across both processors to get access to both networks can give you better performance. So these are optimization things we can do in our configuration of our jobs, placement of our jobs, and setup of our jobs to get better performance. But for most things, you don't have to worry too much about exactly how things are configured or set up, because it will just work. When we come to optimize and make sure we're getting the most efficient use of a system, then we care a little bit about how we're running a job and how we're setting up. And we're coming to see that in the placement exercises. Obviously, it's a computer, so it has a set of software installed on it. We are running HPE Cray Linux environment, which is really Scientific Linux 15 with some modifications made by Cray. We have the Slurm scheduler, as already mentioned, and then we have a set of software to enable user applications. So we have 3 compiler suites: the Cray compilers, because Cray computer, and those compilers are the ones that are loaded by default when you log into the system. But we also have the GNU compilers, so GCC, G++, G-Fortran, and the AMD compilers, Clang, Clang++, and Flang. So particularly with the GCC, the GNU compilers, there should be a compiler there which you can use to access the system and build applications if you've got source code, you know, C code, Fortran code, C++ code you want to bring on. There are communication libraries for these high-performance networks, and then pre-installed software which can be useful. So scientific libraries which do optimize mathematical operations, FFT libraries, things for reading and writing data in different formats, and optimized versions of Python and R pre-installed on the system for us. And for those of you who do programming, then there's a whole set of programming tools available as well. So debuggers, profilers, performance analysis tools. As I already said, this is well documented, hopefully well documented on the ARCHER2 website, document website. So you can go and have a look there. I can show you exactly what, now let me just check. I can show you, let me get up a screen and I can show you what the actual environment looks like. As we'll come on to see. Let me find my ARCHER2 login screen and change the font so you can read it better. Okay. Let me just share this one. So this is what my view of ARCHER2 looks like. Actually, if you log in first, you get a nice fancy message and things, but once you're logged in, this is what it looked like. Most of you probably don't have this at the beginning either, this thing base. That just means I already have a Anaconda environment, Python Anaconda environment loaded. Again, you can ignore that. We'll come on to how you do things like that in the Python part, but by default, you don't have it loaded. Just to emphasize, when I've logged in, this is where I've logged into. So I have a user account called Adrian J. It's not very innovative name, but that's what I have. And that's actually in a project called Z19. So this is my account on the ARCHER2 system for doing things with users and helping out. As we've already said, the home file system is you get a reasonable allocation on there, but it is not accessible from the compute nodes. So I have to go to my work file system to do that kind of stuff. And it's exactly the same thing. It's work Z19 Adrian J. This is the project your account belongs to. We have 2 levels of directories here. So it's possible to share data inside your project or share data outside your project. So if I have a look at /work/Z19, you'll see there's a shared directory there. And I can put things in that directory because I'm part of that project, and anybody in the whole system can see those things. And that's useful for when we're sharing outside ARCHER2, our ARCHER2 projects to other people. But we'll also see shared directory at the higher level. So 2 directories in, which I can put things in which can be shared for people just inside my Z19 project as well. So that's, if in case you're wondering why we have this directory structure where we have multiple directories with the same name for the project, it's so we can set up this internal, external sharing approach for different things. Anyway, that's irrelevant a little bit. And then you'll see that when you log into the system, you have to have a set of things already loaded. Actually, I've been in this for a while and I've loaded R as well. But these are the bits of software which get loaded by default when you log into the system. You don't have to worry about them. And then there's a whole list of other software already installed on the system for you. And that's everything from Python libraries, so PyTorch, TensorFlow, Matplotlib, through to bits of software we think are useful for you. So here we've got the Eigen libraries, Adios IO library, MKL, which is the Intel maths library, these kind of things, PETSI, which is another maths library. Application codes, so these are common codes that people use on systems like ARCHER2, so not data science codes, but things like OpenFOAM, which is a CFD application, VASP, which is a materials application, these CP2K and a materials application. So that's pre-installed for a lot of people. And then other software, things like visualization software, profilers, build systems. So there's a whole bunch of things on there. And the programming environments. These are the compilers we have. So you can see we've got the AMD compilers, the Cray compilers, and the GNU compilers in various forms. And actually, you'll see over here we've got GNU compilers 9.3, 10.2, 10.3, 11.2. So there's a whole bunch of stuff that's already on the system when you log in there, and you can choose it using this module command, which we'll come back and have a look at. Give me a second and I will swap back to the actual presentation. Okay, so we have these different bits of hardware. I've already said login nodes are for compilation and general development, things, interaction with the system, but things that don't take large amounts of compute time. Data nodes are for the longer, so the data analytics nodes are for sort of longer running data movement processing tasks. And then the compute nodes are for everything else. Although the compute nodes are a place where you need a project, you need a budget, you need some time on the system. Usage of cores is restricted. And so what does this mean? Well, it means that when you run jobs on the compute nodes, you get exclusive access to those. So every compute node you have, only you are using it, but you need to set up your application so it uses all the cores on that efficiently. On the login nodes, on the login nodes, you can run compilation tasks and things like this, but you only get what we call a fair share. So you can't use all the cores on the login nodes because that would interrupt or disrupt other people's work. And so there's things in place which, if you do start running large, heavy jobs on the login nodes, your application will just not get access to large amounts of resources and will run very slowly. And the data analytic nodes, when you submit a job to them, you ask for a certain number of cores. I want 8 cores to run this, and you get given that 8 cores and memory associated with that 8 cores, and then you can run on those. Okay, what does the batch system look like? Well, we generally write a batch script to submit our jobs to it, and for Slurm it looks like this. There's a good document here which tells us how to use it on ARCHER2. But for Slurm it looks like this. I can specify the job name, how many nodes I want, how many tasks to run per node, and then I specify what part of a system I want to run for with what configuration, my account name. So here, this would be for those of you using the project for this course, that would be TA105, and how long at maximum I want that job to run for. And so this stuff at the top here tells the batch system how to run my job. And then down here, I'm specifying what I actually want to run. So I want to run this program here called XTHI, which we will have a look at in the practical, on 256 workers across those 2 nodes. And that's what the batch system looks like. It is possible to run multiple things inside a single job, and multiple things in the same node. But by default, this srun thing here we're using to launch our applications is blocking. So this here will wait until this job is run before it moves on to do anything else. You can get around that by putting this and at the end here. And that says run this immediately and then move on to the next thing and move on to the next thing. So here I've said I want to run, I've still got 2 nodes, 128 cores per node, so 256 cores in total. And instead of running one thing to use them all, I want to run 4 things, and they'll run all at the same time, but they'll use separate resources. So here this will run 4 different applications, or 4 different versions of the same application on 64 cores each, and that will run 4 things. So, it's also possible to do that on ARCHER2. So once you've been given your 2 nodes or whatever it is you asked for, you can do what you want inside them using this batch system. The wait down here is important because if you don't do that wait down here, then what happens is the batch job will terminate as soon as the first one of these finishes. So we need to wait for them all to finish before it finishes. And it's also possible to do that instead of a single programmatic way like this, we can do this using some batch scripting as well. So bash script here is saying actually I want to programmatically decide to run 256 jobs, each with 1 core, each with 1 process, and I'm going to do that, and that will do exactly the same thing. So you can do the kind of bash scripting, other kinds of scripting you would normally do inside a shell like this to get you the functionality you want. There are some more complicated things you can do with a batch system. And so it may be that you want to run multiple, so data analytics, data science, quite often you want to run the same thing on multiple files, multiple bits of input, or you can imagine a Monte Carlo simulation where you want to run the same application but with just different starting conditions many times. And of course that will be tedious to do manually submitting all the jobs. So Slurm gives you a thing called an array job, which lets you run the same script on different indexes for a range of indexes. So here we can see something that looks very similar to what I had before, except it's got this new thing here called array in it. And it says run an array from for 56 jobs from 0 to 55. Each one of those jobs will take 1 node for 4 hours, a maximum of 4 hours. And then each one of those jobs will run this command here, but passing in a different array ID here. And then your application can do things with this array ID and choose what they do. So it's possible to run a combination of large amounts of the same job using this array functionality as well. Say I want to analyze 1 million files separately. Each file you need to do something with. You could set up a program, a script which analyzes a file and then run an array job with all those tasks in it, and each one would run separately. So that is how we generally use the system. So you write a batch script saying how you want to run the thing, you submit it, and then it's run at some point at a later date for you. And when it runs depends on how busy the system is and how many of the jobs are submitted and all these kind of things. You will have seen potentially here, we have partition equals standard, QoS equals short. And we'll come on to see what these means, but basically there are some ways to make sure our job runs quickly. And if our job uses a small number of nodes or for a short amount of time, then we can use this short quality of service definition, and that there's a dedicated set of nodes which are just set up for that kind of job, and you usually get quick turnaround. You can also use those to get interactive access to the compute nodes. So sometimes it can be useful to debug what's going wrong with an application, to investigate some things, to actually get access to the nodes itself, or to interactively run the job rather than submitting it through the batch system. Now, it's not the normal way we run jobs, because for large jobs, that interactive submission could be waiting a long time before it starts. So you'd have to sit in front of your keyboard for hours waiting for this thing to start, and it's not very practical. But for short jobs, for things, a little bit of debugging, a little bit of investigation, then you can do that using this srun command directly from the login nodes. So srun asks for one node, 2 tasks per node, 1 CPU per task. In the short queue, with a reservation for the short QoS, actually you don't really need this anymore. And then it will run your application directly for you from your command line, and that should run pretty quickly. You can also do an interactive login using this. Instead of running something like Python, you run Bash, and you can get directly onto a node itself, or the first node anyway. If you ask for multiple nodes, you get onto the first node. Slurm is got lots of different functionality in it, so there's multiple ways of doing this. And another way you can do it, so this is a single srun command which can get you to run an application directly on a compute node from the login nodes, or a single srun command, slurm run command, which gets you a bash shell, which you can interact on the compute nodes directly with. You can also ask slurm for an allocation of nodes. So say, can I get 8 nodes for 20 minutes on the short queue? And then when the allocation happens, you can then manually launch srun commands from the login nodes as well. So it's also possible to do it that way. You don't need to know all these things, right? It's possible to get access to the compute nodes to do some debugging and some investigation if things are not working as you expect. There are a couple of ways to do that. The easiest way is using srun, but you can also allocate a group of nodes and run on them as well. So we started to touch on this, but how is the batch system configured on ARCHER2? What does that look like? Well, we have this combination of partitions and quality of service configurations, which specify what can run and where they can run. Partitions are ways of separating out different kinds of hardware in Slurm, and we don't really have large numbers of different kinds of hardware on ARCHER2, but we do have a couple. One is the serial queue down here, which are those data analytic nodes. There's 2 data analytic nodes I mentioned before. And so if you want to submit to those, you need to submit to the serial partition with the serial QoS. And then you can ask for up to 32 cores for 24 hours on that system. That's on the data analytics node. And then there are limits. You can have 4 jobs running at once and up to 32 jobs in the queue, including the running jobs in total. So to stop people being able to sort of swamp the whole system, there are limits on how many jobs you can submit and how many jobs you can have running at any one time. So for the serial nodes, where there's, I think, 256 cores in total, you can have up to 1 node for 24 hours. That's not quite true, actually, is it? You can have up to 32 cores. So you can have up to 4 jobs or up to 32 cores running at any one time. On the rest of the system, the hardware is exactly the same, except for we do have these high memory nodes. Now, the high memory nodes you can just run on a part of the main system, so you get access to in the standard queue. But if you specifically want the high memory nodes, if you need 512 gigabytes per node, you can specify the partition as high memory and the quality of service as high memory, and you'll only get allocated those nodes. Of course, you probably have to wait a bit longer for your job to run because you're asking for a smaller subset of resources to run on. But if you need that 512 gigabytes, you can do that. And then everywhere else, we use the standard queue partition. And then there's a varying quality of service configurations. So the short one, which I've been showing you, you can have up to 32 nodes for up to 20 minutes. And that gives you pretty quick turnaround of jobs. And you can have about 16 of those jobs queued for running at any one time, depending on how many nodes you're asking for. In the normal system, your maximum runtime is 24 hours. You can ask for 1,024 nodes, and you can have 64 jobs in total queued and 16 running at any one time, with a maximum of 1,024 nodes in use by any one user at any one time. I.e., if you submit a job for 1,024 nodes, you can only have one of those running at once. Okay, I know this all looks confusing. You can ignore most of it, but there are times when you'll run up the limits and they'll say, actually, you can't submit more jobs. And the batch system will say you can't submit more jobs because you've hit your maximum limit. But 24 hours can be a bit short for some people, so there is also a long queue for 48 hours where you can submit jobs of up to 512 nodes for 48 hours. And if you want to use more than 1,024 nodes, you can. There's the large scale queue, but then the limits are lower as well, so you can only ask for that for 12 hours, up to 500, up to the whole system. And so there are various configurations of things you may want to do on the system, where you have to choose the correct QoS and partition. Most users run standard. They're using less than 1,024 nodes, and they'll run for 24 hours, and then the job finishes, and then they restart it if they need to. As I say, this all looks complicated. In reality, most of the detail here you don't care about, but just remember that the batch system has limits built into it. So if you try to ask for a large number of nodes, or for a long runtime, or if you want to submit very large numbers of jobs, then you may run into some of these limits, and you may have to choose a different quality of service setting or a different partition for that. Okay, so we've also already talked a little bit about the hardware and the placement and these kind of issues on the system. And had a little look at that. This is another drawing of the ARCHER2 compute node, so 64 cores on the left, 64 cores on the right. It's a single compute node. Each processor has 64 cores, each processor has a network connection, and each processor has some memory attached to it. So there's 64 gigabytes in each top and bottom here. Again, why do we care? If you're just going to fill up all this 128 cores with work, with processors, with jobs, then you don't care. You'll be able to use all the resources and you'll get all the performance. But quite often people try to do what's called underpopulating when they run an application. So they don't run 128 things on the node. They only run 16 things on the node. And that may be because each thing needs a bit more memory than the 2 gigabytes you would get if you were running 128 things. And so you underpopulate because you want to access more memory per running process, per program, than you would get if you filled the whole node up. And then we do care about we put things, because say I only run 16 things on this compute node, by default the batch system will put all 16 things in this first box here. And again, that will work. You'll get access to all the memory and all the network connections, but some of that access will be slow because you have to go from here across to this processor and get access to the memory over there. Or you have to go from here across to this processor and get access to a network down this path here. And so if you're underpopulating, what you actually generally want to do is, instead of putting all 16 workers in this example here, you want to put 2 workers on each one of these green boxes, spread them out across the nodes. Each worker then gets access to a fast stack of memory. Each worker has a network connection close to them, and we get our best performance that way. So again, most of the time you don't care, probably, but if you're going to run less than 128 things per compute node, then we need to care about how we do that. And so here's our example from before. Here I'm asking for 128 tasks per node, 2 nodes. I'm running 256 things. I've filled up my nodes. I don't need to care where my data is. If I was then going to run this in a slightly more complicated way, I'm going to ask for 2 nodes. I'm only going to put 64 things on each node, 64 workers. Each worker is going to get 2 tasks, and then I run it like this. This will actually do what I want it to do, because I've specified each worker gets 2 cores. It will spread them out across the nodes. And so if you then want to do something more complicated than that, for instance, here I'm asking for 1 node, 64 cores per node, 2 cores per worker, but actually I'm then looping over 8 jobs doing different things. I then have to be a little bit more careful and generate a binding of CPUs, of workers to cores, so that it spreads it out across the node rather than tries to put them all in the same place. But I can do that. There are tools out there, this thing called GenMask CPU, which lets me do that as well. So, you know, again, there's a lot of complexity here. Most applications, most users don't care about it. But if you're ever running things where you're using less workers than there are cores per node, then you need to think, am I spreading my workers out in such a way that will give me good performance? If not, can I go and have a look at the documentation and work out how I do that? And we'll see in the practical session, there's a small program that this one here, XTHI, which prints out what your placement, what your workers configuration looks like, and that can be useful for investigating these kind of things. For storage, for our file system, as we've already discussed, work is our main place we store data. It's a big parallel file system. To get best performance, there's some different configurations we can do. One thing we can do is we can what we call stripe or split our files across the storage targets in the file system. And that's useful for us if we have a large parallel application with lots of workers trying to access the same big file, because that splits up the file into parts, and then each worker can access a different part separately. And this is what we call striping. So striping helps performance on the file system if we have big sets of workers trying to access one file, and they're going to use different parts of that file themselves. However, striping increases overheads on the file system, metadata overheads. So by default, we don't turn it on. So the default stripe count for most files is 1, which means it's not split up across all these disks in the file system. It's actually just located on a single disk. Why do we care? Well, it depends what applications you're running. As I say, if we're running a big parallel application where all the workers are going to use the same file and potentially they're all going to use different bits of that same file, then to get a good performance out of a system like this, of our parallel Lustre file system, we want to split that file up and we want to stripe it. And we can do that here by you can specify the striping using these commands here. So you can set the striping on a directory, and here we're specifying we want the stripe to start to be maximally split up. So -1 means split our file up across all the storage elements we have in the file system to spread it out as much as possible. And we set that on the directory. And then any files that are created inside that directory, once you've set the stripe, will be split up across those chunks. And here we're doing exactly the same thing, but actually we're splitting it up across one chunk, so it's going to stay on one target and go nowhere else. And so if we have an application which has got large files used by all the workers at once, and they're going to be using different bits of that file, then splitting it up, striping it across all our storage targets is the way to go. If, for instance, as you see in data analytics, actually have lots of individual files and each worker works on a separate file, then we don't want to stripe it. We want to use the default configuration we have where our data is, each file is on a separate worker, a separate storage target, but they're not interacting in any way. So, we only mention this because it's useful to come back and think about when you have a use case to use ARCHER2, what does my file, am I spending a lot of time reading and writing data? Do I have to read and write large amounts of data? And if so, what kind of configuration of a file system would make sense here? Do I have lots of independent workers working on separate files? Then I can just use the default configuration and not worry about it. Or do I have, an application with large numbers of workers inside the same application using the same files? In that case, I probably want to split it up and stripe it across and make sure I'm getting the best performance out of this file system that I can. And then beyond that, we don't have a slide on here because this is very sort of bespoke for each use case. You have to request access to it. We have a solid state file system, which is configured in the same way. It has this Lustre file system. It stripes data across it, but it's even faster. So if your applications are really IO dependent, have lots of data to read and write from storage, then we should also consider looking at asking for access to this solid state file system and doing IO optimization there as well. But it follows the same principles as here. It can also split up data across the different storage targets. And if you've got lots of individual files worked on by separate workers, you wouldn't want to do that, and by default is not to. But if you have small number of large files worked on by everybody, then you may want to stripe them across the workers. So ARCHER2, we've got a pretty standard hardware across the system. There's not really much difference, except that we have some large memory nodes which have more RAM in them, more temporary storage. But how you use that hardware can impact the performance. So spreading out our workers across the node, if we're not going to use all the cores, is a sensible thing to do. Spreading out our files across the file system, if we've got lots of workers accessing the same file at the same time, is also a sensible thing to do to give us good performance. And we generally have a batch system set up to access the hardware, which is generally used in a pretty default way, which is configured to run a small number of large jobs. But if you have other use cases where you want to run a large number of small or serial jobs together, then we can use things like array jobs or S-run loops to fill up the nodes with separate jobs and to run large numbers of the same configuration of things automatically for us. Now, this isn't something that people often do who are using large parallel applications, but for data science, data analytics, and even machine learning workloads, this kind of configuration of jobs is much more common. So really, the system is pretty straightforward and pretty standard for a large-scale, high-performance computing system. Has software installed that you need to use, etc., etc. But for each use case, it's worth thinking, how am I going to use this hardware, and where are the things I would need to do configurations to ensure best performance, and then take it from there. But in general, the nice thing is it's pretty easy to get most things on the system and get them up and running, and then you can work on optimizing their performance and making sure you're making the best use of the ARCHER2 system and the hardware. So predictably, we're over time. So we have a practical session and also a break. So what I would suggest here is, you've probably heard me speaking for long enough. We take a break for 15 minutes and come back at 11:30, and we can have a look at the practical session. For those of you who potentially are super keen, then what we're going to look at first, if you go to the GitHub, we're going to look at this practical one first, the exercise practical one, and so there should be sufficient introduction here to tell you what we're doing, but basically we're running this application that I've introduced already, XTHI, to see you can get up and run on the system, and then have a little look at placement, so you can see how you can vary the number of workers and the configuration of the application to see how that works on the system. So you can get a feel for how you spread your workers around if you're going to underpopulate. And you can also run this, there's another code here called streams, which is a memory benchmark, memory performance bandwidth benchmark, where you can see actually what performance impact do you get if you don't spread your workers around, or if you do spread your workers around, you know, what's the best and worst memory performance you can get. And a lot of application performance is really limited by memory performance. But as I say, please do take a break now, and then we'll come back at 11:30 and we'll spend 15 minutes on this, and then get on to the next lecture. And in the meantime, if you're having any problems getting onto the system, you've not managed to get a login account, you've not managed to log in, you don't understand anything I'm saying, anything along these lines, now's a good time to let me know here in the chat or on that Etherpad we have as well. Thanks. So basically, at the moment, we're just going through this PDF, getting on the system, running this sample application, trying out different configurations of numbers of workers, which we call processes, and number of threads for those workers, which are like little mini workers per process. And then at the end, you can try a memory benchmark to see the different memory bandwidths you get when using different configurations of processes and threads, and spreading them around the nodes or not spreading them around the nodes. So have a play with that for about the next 10 minutes. Let me know if you have any problems. Let me know if you have any questions. Me and William are around, so we can help out with those. And then we'll get on to the next lecture. Yep. That's a great question. Do you need to edit CPUs per task in order to get more threads per task in addition to exporting the OMP threads? So technically, no. You change OMP threads, that will create more threads per task. But if you don't change the CPUs per task, then those threads will only use the CPUs that have been assigned to that worker that's creating the threads. So say you create 4 threads and you've only got 2 CPUs per task, then those 4 threads will be sharing those 2 CPUs, or 2 cores in this case. So to get good performance, what you want to do is also change your CPUs per task to match the number of threads. So it's a good question. The question here was, what does affinity mean? When it says affinity equals 0, 1 to 8, affinity equals 0, 1 to 8, affinity equals 1, 1 to 9. In the output of the XTHI application. So basically what's specified in the affinity there are the cores that this thread is bound to, is able to use. Now, I didn't go through it in this level of detail, but actually each node has 128 cores. But each core can run 2 threads, what we would call hyperthreads. And because of that, there's actually from 0 to 255 cores, what it calls cores, inside a node. So basically this is saying that on node 0, rank 0, thread 0, it has access to core 0. and the hyperthread of that core, which is called core 128. And then for node 1 and node 0, rank 0 of thread 1, it has access to the same. So basically, we've got two threads sharing a physical core, but both able to run at the same time. And so this is what we're seeing here is we effectively in this here, each physical core is being doubled up to use by two threads. Now this can be okay, or this can impact your application performance, depending on what your applications are actually doing, but that's what it's saying. Okay, I'll just briefly discuss what the practical, and then we'll get going on again. If you have any questions, let me know. So this was really just an exercise to make sure you could access the system and run jobs on the system. If you've not been able to manage to do that, then do let us know, let me or William know. We can still help you out with that. It's useful to be able to get you on the system and get you playing around with the actual hardware and software we have here. But it's also useful to play a little bit around with that placement stuff and notice that you have control of where things go in the system when you run jobs, and making sure that you do that placement correctly or sensibly can give you good or bad performance. And the example here was, which I've got here, I'm in this streams directory from the binding example, and streams is a memory benchmark, and I've run this 3 times. We'll come back to that directory issue in a second. You should already have a directory in /work/TA105/TA105 with your same as your username. So if you did this command, it should work for you, I think. Get you to the right place. If not, then something's gone wrong with setting up the account, but it should be there. So I ran this 3 times. The first time I ran streams, I was using all the cores on the node with 128 workers. And here you can see that for my benchmarks, it's maybe not clear, but I run this a lot, so I sort of know what to look for. I'm getting about 220 gigabytes a second of memory bandwidth for the best benchmark. Okay, so that's the sort of details there. So that's what the kind of, it's not the best performance you can get out of nodes, but that's what you can expect. 220 gigabytes a second of data you can move to and from memory. If I then underpopulate and only run 64 workers, so now I'm running 64 workers, 64 processes per node instead of 128. I can see that I've got less than half that, so I'm getting at best about 92 gigabytes a second. But there I was running, and I wasn't telling it, I wasn't spreading my workers out. So here, when I got that exercise here, I had 64 tasks per node, and then I'd set CPUs per task equal to 1. And so if I change that and then set CPUs to task equal to 2, spread out my workers, so I'm using both the processors, both the data across the memory across all the nodes, then I can see I can push that 93 gigabytes up to 110 gigabytes a second, or half the bandwidth we had before. And so you can see that this placement has an impact here on performance. With this benchmark, I can improve my performance by 10–20% by making sure I'm using the resources efficiently across the node. And you can play around with this more. You know, actually, I can get better performance if I have less workers and more threads, and make sure they're spread out. I can get probably up to about 250 gigabytes a second. But that's the kind of things we're looking at. Got any questions or comments about the exercise? Okay, well, I'll load up the next lecture and we can start on that. So the next lecture is meant to finish. Oh, well, so we have this lecture and then an exercise, and then we finish for lunch at 1. So we should still be able to fit these things in. With maybe you'll need a little bit more time for the exercise after lunch as well. So we'll break it at 1 for lunch. But now what I want to talk about is containers. So that was sort of hardware and a little bit about the software in the system. Let me just open up my next lecture. Okay, software install and containers on ARCHER2. Now again, for a lot of users of ARCHER2, people who are in the scientific space, computational simulation space, I should say, we're probably all in the scientific space, but people who are using ARCHER2 for large-scale parallel applications to run simulations, actually a lot of this stuff you often don't have to worry with because the software you want to use is already installed. You want to use a package that other people are already using on ARCHER2 and it's already available. So they just have to get on, learn about your batch system, understand how to submit their jobs, and they could go and run. But for people bringing new software, but for people doing things like data analysis, machine learning, these kind of things, quite often actually one of the hard tasks is to get your software onto a system and up and running and installed and working for you, because a lot of, particularly in the data science field, a lot of software is sort of designed for installing on local machines rather than on large shared systems like ARCHER2. Okay, so ARCHER2 already has software installed in it, and we can access that through using this module environment. Modules is not anything magic. All it does is it sets up some environment variables which lets you access installed software. Actually, under the hood, all it's doing is setting some paths in the shell you're using, which can then be searched if you ask for an application to be used or if you ask for a library. But it is a convenient way because you can effectively load and unload software to use. And one of the ways we do this is with the programming environments, and so we can use these commands: module avail, which I've shown you before, which lets you know what's installed on the system already; module list, which will show you what software you currently have loaded; and then module load and module unload will load and unload new software. So module load prog env GNU, which you have here, is something which tells you, which sets up the GNU compilers, the GNU programming environment, so GCC, G-Fortran, G++ for you. Of particular interest to this course, there's also Cray and R versions, which are centrally installed, which contain some optimized pre-installed libraries for you. And so actually, I've not checked this recently. Let me just check what the Cray, I think it's still 3.8, but that might have changed. Let me just so I can show you what I'm going to do here just to check. Stop sharing this, and I shall share my command line. So if I clear this, if I do module list, what have I got loaded? I don't have the module, the Cray Python module loaded, so I'm going to load that up. If I do module list again, you'll see I now have Cray Python, and it's Cray Python 3.8.5. I can see if there are any other Pythons available from Cray by saying module avail Cray Python, and you can see actually, yes, Cray Python 3.8.5 is the default version. That's what the D means here, and I have loaded it. But there is also a couple of newer versions, 3.94, 3.97. I think 3.10 will be coming with the next software upgrade shortly. So this gives you a version of Python that's been optimized on the system to use things like fast maths. I'm getting ahead of myself again here a bit on the slides, but fast maths libraries for some of the functionality. I can actually see what is in there. So module show Cray Python will tell me, will give me a setup of what's going on. So it says it has Python, NumPy, SciPy, MPI for Pi, and Dask all installed for me, which is set up to call the optimized Cray maths libraries called Cray libsci, and the optimized communication libraries Cray mpitch for us. And there's a lot more, there's more documentation going on there. I can also do the same for Cray R, and it will say this is the 4.0.3 release, and these are the kind of things that are installed with it. So if you have to bring your own software onto ARCHER2, what are the challenges? Cray Linux at some level is pretty standard Linux these days, actually, Scientific Linux 15, but it's not your Ubuntu, it's not the default flavor, and you can't just do an apt install or a yum install directly into it. So you have to take what's already installed and build on top of that. So it may not have the dependencies for your software installed. And the default home directory, the other challenge is if you build code in /home in your workspace your file storage that you log into, that's not available on the compute node. So we need to make sure that we install any software we need to use on the work file system so that we're able to access it from the compute nodes if that's where we're running. Cray has a bunch of scientific libraries, which include the BLAS libraries, the LAPACK libraries, and the SCALAPACK libraries. But there's also other ones in here that are installed, FFTW, PETSI. We've already had a look at these a little bit. But there are a whole bunch of maths libraries installed, which give you optimized things like matrix, vector operations, and higher order things. There are 3 different compilers, the AMD compilers, the GNU compilers, and the Cray compilers. The way ARCHER2 is set up, actually you call them all in the same way. So if you want the C compiler, you use CC, lowercase cc, and that gives you the C compiler. If you want the C++ compiler, it's uppercase CC. And if you want the Fortran compiler, it's FTN. And that name doesn't change. But if you want to use the GNU compilers, you load this GNU compiler environment, module load program GNU, and that gives you CC is GCC, CC is G++, and FTN is G-Fortran. And if I loaded the Cray compilers, then these would be the Cray compilers instead. And if I loaded the AMD compilers, those would be the AMD compilers instead. So I can give you another quick demonstration of that, just to make it clear. Hopefully make it clear. So if I clear here again, module list, I've got the GNU programming environment loaded at the moment. So if I did CC -v, it says the C compiler is GCC version 10.2.0. And you can see that's GCC 10.2.0 loaded with this environment here. If I did a module load prog Cray, it does a bunch of stuff. It replaces GCC with the Cray compiler and the program environments. And then if I do the same thing now, we can see CC -v, Cray Clang version 11.0.4. So this is how we play around with compilers. But the compiler names themselves don't change. We can just load in different compilers. Okay, so if you have to install your own software, particularly if you have to install Python or R, we'll come back to R, but you have to install your own software, we need to make sure we do it in the work file system so we can access that software from the compute nodes. You can do this in Python by just setting up your Python user base environment variable to point to where you want to install. So you load the Cray Python environment, and then you do export Python user base equals, and then you put in here your work file system location. So I've made one up here. That's this work in the T01, T01 and the username is a user, but you could replace that with whatever you wanted. For me, at the moment, it's work Z19 Adrian J, and then you specify where you want to install stuff. The default on these systems is into somewhere called .local, directory called .local, but you could call that anything you wanted. And when you've done that, you can export the path, so you can access any executables that are installed, and then you can just use Python as normal with pip installs and virtual environments, and that will automatically install everything into /work. So you activate a virtual environment, you install stuff, and it's there. Some Python installs, even using things like pip or conda, will need for you to set the compiler variables to pick up the correct compilers. And you can do this by using these export commands down here. So tell it what the compiler names are. For R, we do the same thing, but here we now use something called rlibs user. And again, we specify a directory where we want that. So here, this is an example with my specific setup, work Z19 Adrian J, and I put everything into something called R install. But again, you could have that as .local or whatever you want. And then you can just install stuff inside R as usual, and it will go into the right place. There is again, you may need to set up the compilers so R, if it's building packages, knows what it does. To do this, you have to do a bit of manual work. So you have to create a directory in the home file system called .r, and then a file in this called make_vars, and then you add these things in here, these command lines into this make_vars file, and that builds. Now you'll see this is on the home file system. This is not accessible from work, but this is just for building software, which is what we use the login nodes and the home file system for. So that's fine. It'll pick up the preferences from there, and then it'll install it into where you've specified, and it'll do the right thing. So here's an example of installing RMPI. I can specify some configuration arguments, and it picks up the right compilers here. By default, in the R thing that was already installed, there's a bunch of libraries already available for you. So these are ones installed. You can actually look at that yourself by running rscript -e install.packages like this. But that's it. So if you're installing default flavor Python stuff or default flavor R stuff, you can build your environments using these methods and just use it as normal. Anything which is beyond that, which won't install or you have trouble with, then we can use something called containers. And you may have heard of Docker. Docker is quite a commonly used system. Kubernetes has some involvement in this as well, but Docker is a container format, and it's an example where effectively what you do is it's like a virtual machine. You get a defined operating system to run inside, and you can configure that operating system for what you want to do, but it's a bit more lightweight than full virtual machines, than a full VM, and it sits between the host operating system, Scientific Linux in this case, and your application. So it's a way of getting a view of the system in software that looks like what your application is looking for, and running that on top of the existing operating system we have. So formally what it does, it separates kernel and user space and lets you define a user configured kernel space to do that. We use so Docker is commonly used at a lot of places, but it has some security issues on a shared system like ARCHER2. So we use one called Singularity instead, and that is designed for high-performance computer systems. It isn't the only one. There are other containers out there, Shifter and Charlie Cloud and Aptena. But we use Singularity, and this is already default installed for you. And what you can use with that is you can go and get a Docker container or your own container and set it up and run it here. So here's an example here of running a Docker container and on the system. So here and if you've never done containers before, don't worry that you don't understand any of this. it will come to be, it should hopefully make sense as we go through. But here we're using Singularity to get a container. We're going to call it Python 3.9.9, and we're pulling it down from this location online. And then once it's come down, we can then just run Python inside that. And so you can see here that if you wanted a newer version of Python was available on ARCHER2, it might not be optimized in the same way, but you needed it, you could get a container with 3.10 and pull that down and run it inside that. There are also containers, predefined containers, so you can think of these as operating system configurations. On other places here, so there's a place called datasets.datalad.org. This is really what's called a Singularity Hub, and we can pull containers down from there as well. So you can have a look for existing configurations of base operating systems that your application would run inside and run that. Singularity then lets you run the container, get a shell, so interactively work inside the container, or execute another command on top of a container. So this is really how we generally use it. You execute the container and get it to run this command at the end here. Now we have a set of containers already set up on the system, so /work/y07 shared Singularity images is a set of containers which are set up to do basic things on the system. So there's one which is sort of a basic MPI version, but on a Linux setup, which is easier to use. And there's a Hello World one, there's a Python one, there's a couple of Python ones, and there's one for benchmarking the communication network as well. So you can have a look at them and see what's available there. By default, when you launch one of these, you get your users and groups from the host system, and that lets you get access to the files and the directories of the underlying file systems there. So here's an example here. I'm using a Singularity shell of this. So I'm getting a shell. I'm interactively using the container. I'm using this Hello World one, which there is an example of here, which you can pull down in the example. And you can say, who am I? And it knows I'm Adrian J inside this, and it knows I have access to these specific groups, because by default it's picking these up from the base operating system. But what containers don't, what Singularity doesn't generally do is import the full file system. Okay, so it doesn't generally bring in anything except your home directory. So when I run Singularity on a container without any other commands, I generally only get this home directory and stuff inside it. I don't get anything else. So we can get around this, and of course we need to get around this because the home file system is not accessible from the compute node. We can use this bind flag, this -B flag, which binds a directory into the container. And then when I run it, I can access everything that's inside this directory as well. And I can actually rename those kind of things inside the container as well. So I can specify a bind path, and then inside the container, this will be called work dir rather than this whole long thing here as well. Now, it's important to know that containers are read-only, except your home directory and bind directory. So you can't, when you're running a container like this, you can't change anything inside it, but you can change the directories you bind into it. So this is an example here of how I can run the containers on a compute node. Now this changes whether you're running it across multiple nodes and need to use the network, or if you want to use it inside a single node. So here's an example. If I just want to run my container, my application inside a single node using all the cores or whatever inside the node, I can just run it like this, Singularity run container name, and that will work perfectly fine. If I then want to go across nodes, if I want to use the network and do MPI and or more complicated things, it gets more complicated. You have to specify specific library paths and bind things correctly, and you have to do all this kind of stuff. This is complicated, but the thing is you don't have to know how to do it. You can just copy this recipe and once you copy all this stuff from export here down to bind ops here, you can then just run your container as you would normally, and it should just pick up the networks fine and run sensibly. Again, most of you probably won't be building containers to run MPI tasks like this, but it's useful to know that it's possible. And you can, so MPI tasks are things that are communicating across the network. It's possible to do it, and that is available on the system, and there's good documentation, and we can help you do those kind of things if that's what you end up having to use. And so here's examples. Here I'm compiling my application using the compilers from inside the container, like this, and I'm running my application interactively using the container to run across multiple workers here. And this MPI thing is, so if we want to use containers to build an application which communicates across nodes using MPI, which is the library we tend to use for large parallel applications, it gets quite complicated. But we don't need to go into massive details about that here. You need a specific container set up with the right MPI installed on it, and there are definitions. Here's an example of a container defined, a container recipe, which is building a Ubuntu operating system, but setting up the MPI libraries so that they can work on the ARCHER2 system. And so you can use this container to then, which we'd take this recipe, save it into something called OSU benchmarks def, and then build a container using that, and that would let us do that kind of thing. Again, this is probably more detail than most of you need, but just be aware that if you need to build containers with specific things inside them, and you need to parallel applications, it's possible, it's just a little bit complicated, and you should have a look at the documentation or come and speak to us about doing that. The downside of containers is that to modify the container in any way, so like install new software in it, these kind of things, generally you need root permissions. So you need access to a system where you have root access, so you have the permissions to sort of install things centrally, and then you can modify the containers and build your image, your container, and then copy it across to ARCHER2. It's harder to do that. You can't do that on ARCHER2 itself. You'd need to build it locally and then copy it across. The good thing is that there's lots of custom containers set up already out there that you probably don't need to do much changing, and you can probably just use them as is. So that may be relatively complex. Apologies if it is, but the main takeaway here is that ARCHER2 has lots of software set up for it. For data science, ARCHER2 has lots of software already installed, which is probably useful, particularly Python and R installs. If you need to add things on top of what's already there, that's perfectly possible. You can do that using your standard ways you do this in Python, using Conda, using pip, but you need to make sure that you install them in the work directories and you set up Python or R to understand that's where you're doing it. And there's specific ways we do that. And then beyond that, if you have more complicated needs, then containers is the way to go, because that lets us set up a full operating system different from the one that's running on ARCHER2, and then host your software inside that. And that can get around things like installing dependencies which are not, you're not able to install on ARCHER2, or installing with older versions of software than we have, and these kind of things. Now, the only caveat I would say is that there are two places that performance may come into this. If you're using containers with old versions of software, then it may be that you're not going to get the best performance out of the system because you're not getting all the optimizations that have come into newer versions of compilers and newer versions of MPI and communication libraries, newer versions of softwares themselves. And the same thing's true as if you're using something like Conda or pip to install things on ARCHER2. It's not always possible to control them enough so that they pick up the best maths libraries and pick up the best configurations. So the Cray installed NumPy, for instance, is likely to give you better performance than installing your own version of NumPy on Archer 2. So that's why we would suggest that if you can use those central installs. And if it turns out you take your application on, you're installing your own things, it's always worth having a little look at performance, making sure you're getting sensible performance, and if not, coming to speak to us and seeing what we can do to help you improve the performance on these kind of things. For little applications, for things that take 2 minutes and you run on the login nodes, don't worry about it at all. This is only really important when you're installing things that are going to run for large amounts of time using lots of compute nodes, and that's where we want to make sure that we're getting the best performance out of the system possible, so that we're efficiently using these high performance resources we have. And that may mean things like the binding and placement, but we looked up in the last lecture, but making sure we get the best maths libraries, the newest compilers, the best compile options for a system like this. But it's an iterative journey, right? You start, you port, you make sure your application can work and can run on Archer 2, and then we can look at improving the performance. Any questions? Well, it's good because we've caught up nicely. We've caught up nicely with where we should be, and so we can now move on to the second exercise, which is to look at using containers on Archer 2. So trying out this container idea on the system. Oh no, actually, that's the third exercise. So the second exercise, sorry, is to look at file system performance. So we didn't do that before the break. So we can. There's 2 exercises you can now do between now and lunch, between now and 1 o'clock. One is to play around with file system performance a bit and look at that striping versus non-striping and see what performance benefits that can give you. And then the other one is then looking at software installs. So can you install Python things properly? Can you install R things properly? And then so you can use them from the compute nodes. And then can you play around with containers and how do they work? And what do they look like on Archer 2? So let me just share again with those with you, and then we can let you go on and play with the practicals. So it's practical 2 and practical 3, and I'll just share the PDFs. So practical 2, you'll see, is about file system performance. So there's a directory called IO in the exercises, and again, this is a little benchmark here, which just does file IO, reading and writing data to files. How fast can you do it? And you can play around with setting the luster stripe to see if that improves or reduces performance. Okay, so that's a quick little exercise you can do. And then if we go back to exercise practical 3, here this is use CreatePython, set up your Python user base, install something we'll use later, so DAS distributed, and try checking that works from the compute nodes, do exactly the same thing for R, check that works from the compute nodes, and then have a look at building a container and using a container on the system. And we've got that now until 1, break at 1 till 2, and then when we come back at 2, we'll look at Python and Dask on Archer 2, and then after that we'll have a practical and then look at R and parallel R on Archer 2 as well. Any questions? If not, then feel free to play around with practicals. As I say, I'll be here till 1. and then we'll take a break till 2 and then come back then. But give us a shout if there's anything that occurs to you, anything that doesn't make sense, anything you've not understood so far, please let me know.